Matrices are also used, and just roughly giving an idea, if you have a matrix A which could have be n by n matrix, you can use indices I and j, and they represent ith and jth element of a matrix A. Okay, and matrices could be also used to represent different problem, and in fact towards the end I will show you how a matrix can be used to represent a linear programming problem. So again, one of the other things that I want to quickly mention, that sometimes you have a vector which is resulting from a multiplication of a vector to a matrix, right? So there is a matrix and you multiply that matrix, and that also results in a vector. So in that sense, sometimes matrices are considered as a transformers, which basically takes input one vector and transform that into another vector. Now when we are doing this transformation, if the vector y is of size m, right, and if the vector x is of size n, then the matrix A has to be of the size m cross m, and the dimensionality has to be matching this, so that when you multiply m cross n with a n vector, it results in a m vector, m dimensional vector that is out there. So one of the things that I want to do with this is basically, this equation we can write this yi is equal to aij jx, right? So using from this equation that is out there, this is written in essentially the indices format, right? Similarly, you can write the same, this equation, or this is expansion of this equation in a vector form, where your vector y is given as summation of a vector j multiplied by xj. And essentially what you're seeing is a linear summation of the column of the a's multiplied by the individual x's. That is what is happening, and that's how you're arriving at a y vector. So the right hand side is essentially a linear combination of column of matrix A that is out there. Okay. Sometimes when the problems are quadratic in nature, you will also see double summation, and that's why it's important to discuss the double summation idea. So the double summation is like you have a vector x transpose y, x transpose that is multiplied by y, and essentially it's an inner product of x and y. This is something that we have discussed in a previous notation, and that is going to be essentially equal to I equal to 1 to n summation of that times where the the element inside that is xi yi. Now what happens if this y is basically given by this equation, right? So if you have this equation, then I can substitute this y equal to ax, and I will get a double summation, or what is known as the triple product, and that is something that occurs sometimes in the optimization, especially when we are objective function or the constraint functions are quadratic in nature. So let's go through that. So again, what I'm doing is I'm taking y equal to ax and I'm substituting this ax right here. So that's why you will see that x transpose multiplied by y is substituted by x transpose a multiplied by x, which is known as the triple product. We have this, and this is something that you will see in quadratic programming a lot, right? This equation will come in the quadratic programming a lot, but I want you to see how this could also be written in the index format, right? Sometimes people write that in a triple product format, but the same thing could also be written in the indices format too. So let's go on and see how that could be written, right? So again, what is this, right? X, you can see we can take this, which is xi, and multiply this ax, which is basically j equal to 1 to n ai xj, which is from here, and we can bring that here, and then that will essentially give me this final equation. So as you can see, there are two terms of x's that are multiplied together, and you have two summations. So that is also known as double summation equation or triple product equation. And then as you can see that there are two x's, and essentially if you expand this, right, you will have terms like this, which is a11 x1 squared, a12 x1 x2, and so on. And essentially the equations are going to be quadratic, right? The power, the degree of this equation is 2, and essentially it will result in quadratic equation, quadratic sort of equations that you're interested in. Okay, so we can go ahead, and we can, the final notation that is typically found in optimization literature is product, which is pi I equal to 1 to n xi. That means we are basically multiplying x1, x2, x3 up till the n times, right? So this will basically create a polynomial of nth degree where all the terms are multiplied. And this is something that you will see in geometric programming a lot. So if you are involved in geometric programming, which is the class of optimization problem, then you will see the product notation too. Okay. So with that, I think these are like the main notations or main equations that you will come across in a lot of optimization book. And what I want to emphasize is, you can see that you can have two different formats. You can have a vector way of writing a optimization problem, and you can have an indices way of writing an optimization problem. And these are the two main paradigm. Essentially, you can see they are exactly the same thing. So I just wanted to cover that aspect in this quick way, so that you are aware that if you see something like this and you don't see like this, then you are not confused that you are dealing with an optimization problem. So there are two different main ways that our optimization problems are typically written, and these are the two ways that I wanted to discuss. So with that, let's move on to discussing what are the different classes of optimization problems.